This video will cover the third page of notes for the topic of exponential and log equations. For this video, we will go over how to solve exponential equations as well as logarithmic equations, as well as do a couple examples. First, let's review how to solve exponential equations. We have two types. One type is where the bases are already the same. If that's true, then all we need to do is let the exponents equal to each other. The second one is when the bases are different and I have my x in the exponent that I need to find. So one of the things we can do is to take the log of both sides and then use the third property of logarithms to bring that exponent to the front. Let me show you what I'm talking about. I would do something like the natural log of a with the exponent that has an x in it is equal to the natural log of b. Then I would use that third property of logs to bring this exponent to the front. So now I would have f of x times the natural log of a is equal to the natural log of b. Then I would divide both sides by the natural log of a, the natural log of a. And in doing so, what we find is that f of x would equal to the natural log of b over the natural log of a. Then all I have to do is solve for x. We have also discussed how to solve log equations. That means we have log in the equation. So we found two types. One is when we have a log on the left side and a log on the right side, as long as they both have the same base, whatever that base is. I do want to remind you that even though a base was not written, we know we are talking about the common log. In this case, both of them would have the base of 10. When you have one log on each side, then we can kind of ignore the log and then just say that x is equal to y. Very similar to the idea that we had up here when we were talking about exponential equations and they had the same base. What we need to remember is that the log property here that we're discussing is because the log of x is just the exponents. The log of y is just the exponents. Since the bases are the same, then we can say x and y are also the same. And finally, the last type of problem we had is when we had to combine using our other properties of log to combine two logs to make it into one log. Then we would have one log on one side of the equation and a constant on the other. Then the easiest way to remember how to convert this or solve this is to put it into exponential form. We have our base to our exponent is equal to an argument. So then from here we can start solving for x. Let's do a couple of examples. Let's do example number 1. Here we have log of base 7 of 23 is equal to x. The other thing I want to remind you is that maybe we might see this as a problem that says log of base 7 of 23, and our job is to evaluate this. Either way, I would sit there and set it equal to x and then start solving. So if I come back up to the top of our page, we can see that we do not have an exponential scenario, but a logarithmic scenario. I only have one log on one side, so that means I need to worry about this part right here. We have one log on one side, and we have it in this format that we have here. Our job is to rewrite it as an exponential. So remember, here is our base to this exponent that will equal to this argument. So I'm going to have 7 to the x is equal to 23. Now I have an exponential problem, and our two choices for exponential are, do I have the same base or can I get to the same base? And if I don't, that's okay, but then I would have to log both sides. So let's come back to our problem, and we see I have 7 and 23. Since I don't know 7 to what exponent would equal to 23, I'm going to declare that I have different bases. So I'm going to take the log of both sides. In this case, I decided to take the natural log of both sides. When I take the natural log of both sides, that gives me the natural log of 7 to the x power is equal to the natural log of 23. Then I'm going to use the third property of logs that says I can bring my exponent to the front. So now I have x times the natural log of 7 is equal to the natural log of 23. Divide both sides by the natural log of 7. And I find that x is equal to the natural log of 23 divided by the natural log of 7. And we would leave it like this because it is an exact value, as opposed to putting it into our calculator and getting an approximate value. This one also is the same type of problem we would use for the change of base formula. Since I'm not into memorizing formulas, I just use my techniques for solving log and exponential equations. Now let's do example number 2. We have 1/2 is equal to e to the 5x. If we come up here, we realize that we have this second case of exponential equations, where we have 1/2 on one side and then we have e with our exponent containing our x. So we have different bases, so we're going to take the log of both sides. The hint to the wise here is that since we have e as a base, we should use natural log in order to solve this problem. When I take the natural log of 1/2, that's the left side, is going to equal to the natural log of e to 5x power. Using the third property of logs, I'm going to move my exponent to the front, so I'm going to get 5x times the natural log of e, and that still equals to the natural log of 1/2. What we find out here is the natural log of e is equal to 1. How do I know this? Remember that natural log is the same thing as log base e of e, and I claim it's equal to 1. If I use my power, it would be e to the power of 1 is equal to my argument, and that's how we see that this is equal to 1, this is equal to 1. So if we need to remember anything, is that the natural log of e is equal to 1, and 1 times 5x is 5x. So now I just need to solve natural log of 1/2 is equal to 5x. I'm going to divide both sides by 5, and I find that x is equal to the natural log of 1/2, the whole thing divided by 5. I would leave it like this as an exact value. If I was going to put it in my calculator, I would have to remember to put parentheses after I finish entering the natural log of 1/2 before I put the division bar and divide it by 5. And that concludes this video.